Good evening, everyone. For the participants of the Vikram discussions, welcome again. And for the participants of this PRL-IAPT talk, welcome to PRL. And without much delay, we will begin with the welcome of our speaker of the day, Professor Nigel Mission. And I would like to request to offer a bouquet to Professor Nigel Mission by IAPT RC7 President, Professor Vinod Kumar, sir. Yeah, I request Professor Joshipura to welcome our director, sir, Professor Vardwaj, with a bouquet. And I request Director PRL, Professor Bhardwaj, to welcome President IAPT RC7, Vinod Kumar, sir. Yes, thank you, sir. I would like to request and welcome Director PRL, Professor Anil Bhardwaj, to formally welcome the gathering and initiate the proceedings, sir.
So, namaskar and very warm welcome to everyone for the 6th PRL-IAPT Vikram Sarabhai lecture. We started this series of lectures in the year 2019, which is the centenary year of birth of Dr. Sarabhai. And it was a mutual concern between IAPT and PRL with Kamal and Joshipura ji telling that we should start some series between PRL and IAPT to become a lecture series. And we gladly agreed to that. And since then, every year, without any fail, in spite of having COVID, we have been continuing this series of lectures. बजा लीजिए ताली बजा लीजिए. So today we have very distinguished lecturer who is going to lecture on us as a part of this lecture series, which is Nigel Mason. And before that also, we have been choosing distinguished speakers to talk in this series of PRL-IAPT Dr. Vikram Sarabhai lecture. This is also another, what I should say, a special moment for all of us that we are conducting this as a part of another series which we started today morning, which is called as Vikram discussion. And we have been adding this PRL-IAPT lecture series as a part of either a conference or any other event which is happening in PRL, so that both PRL-IAPT and IAPT can take advantage of that. So thanks to the colleagues from PRL-IAPT to organize this as a part of the Vikram discussion today, which is going for next 2 days, today and tomorrow. And once again, welcome to all the colleagues and especially to IAPT colleagues who are present over here, the president and the colleagues of IAPT. May I now request the colleagues to take over and conduct the proceedings. Thank you. Thank you very much.
Thank you, sir. Now I would like to request Professor Vinod Kumar, sir, to give a brief introduction to IAPT RC7 and its activities, sir.
Professor Anil Bharadwaj ji, members of IAPT and distinguished professors of PRL. It is really a homecoming for me here. So anyway, it's a pleasant duty. First of all, I will express my gratitude to our director for readily, without any delay, putting the name for this sixth IAPT, PRL IAPT Vikram Sarabhai speaker. And it all materialized. Again, I thank our speaker who has again agreed readily for this activity of IAPT PRL. From IAPT side, I welcome you all for this lecture. It is my duty to say a few words or a few moments about the, pricing about the activities of IAPT. IAPT, you all know that it is meant for the Indian physics teachers of all level, from school to college to degree to scientists who are working towards the various aspects of physics. It began, in fact, in the year 1984. So it is around 40 years now. So just now we had the first activities of this RC7 Regional Council of IAPT. Few lectures by Professor Yoshibura and one lecture by Dr. Pratul Desai to begin the 40 activities of IAPT RC7. In fact, it was all started with the visionary of late Professor D.P. Kandelwal. With an active support from few physics teachers, it has begun. And today we have reached across more than 10,000 life members of IAPT, varying throughout the country as well as many from abroad. And this is his special year, centenary year of Professor Kandelwal. So last year onwards, we have been celebrating this centenary activities, commemorating the efforts of Professor D.P. Kandelwal. To say a few words about various activities that we conduct at the national level as well as RC level. Activities for teachers, activities for regional council, Anveshika, Asian Physics Olympiad, Center for Scientific Cultures, conventions, evaluation of experimental skills, innovation hub, national competition for innovative experiments in physics, national standard examination at the National Student Symposium on Physics, Olympiads, orientation programs, and faculty development programs. It was recently started by RC07, something very important, two activities. The third one is the faculty development program that the RC7, Regional Council Gujarat 07 has started. The first one is what we are witnessing as the sixth lecture of PRL-IAPT Vikram Sarabhai lecture. The second one is a publication in Gujarati with some percentage of articles in English being published by RC07. And the third one is the ongoing faculty development program that we have initiated for the physics teachers. It is something slightly different than the usual concentrated 15 days or 21 days program. It runs for a period of one full semester, where every Saturday the participants will be discussing various topics, particularly related to a specific books. We have selected this time Feynman Lecture Series, Volume 1. So the chapters are divided among different mentors, and then participants will be discussing with him every Saturday around 2 hours. And at the end, we are towards the end of this, maybe end of January, it will be over. Then all the participants and mentors will be collected for a 2-day workshop, wherein extension of the topics, relevant subjects which are being discussed will be collected as an application, as a problem solving, or as an, a field which will be evolving to the latest field, how these things are related, making a connection. And we are planning to bring out as a supplementary book form, wherein the chapters of those books will be credited to the participants. So participants will be getting a FDP certificate along with an authorship of a chapter along with the mentor. This is what a new edition of the RC07 we have initiated. Now coming back to the main body activities, I have mentioned many of them. The Indian Association of Physics Teachers publishes a monthly journal of around 50 pages every month, which has a record of uninterrupted publication since March 1984. Still it is going on. Besides reporting Indian Association of Physics Teachers activities, including the activities of Regional Council, it also carries articles on developments in physics and physics education. Physics news, what is the latest news of physics research, read for its members, and it also serves as a vehicle of expression and communication amongst the members. It can be subscribed for libraries, for schools and college and universities. Pragami Tarang, as I mentioned earlier, it is the 15th issue which is being published, and it also being received largely by the teachers from Gujarat region. And it is also being appreciated very well by the IAPT main body, IAPT president and secretary at the main body. This year again, we have started to increase the readership of this magazine, Pragami Tarang. We have initiated a quiz competition based on that particular issue. All the articles which are appearing in that will be circulated as a soft copy, and then the registered students, teachers, and physics lovers in general, they can read those articles, and we are planning to conduct a quiz competition. And so far, till today, I came to know that around 700 registration has been done so far. And tomorrow is the last day of this registration. We hope probably around 750 we may cross. And that is a great success because we are just starting this program this time. Probably next year, we may couple this physics teachers journal of that particular month or that year, along with this Pragami Tarang, to have the wider perspectives of the articles, and then we'll circulate at the national level. So we will see that at the national level, just to enhance the reading capacities of the students largely, and then we'll be conducting such a program. That is our proposals, and probably it will come through. Various orientation programs and seminars, workshops for teachers, and at the end, we used to have a national convention wherein many of these innovative experiments designed by teachers are being displayed, and there will be prize distribution for that. The Anveshan is a particular program which is meant for inculcating experimental skill with minimal experimental facilities. The facilities which you are having at your own home, at your own schools or colleges, make use of that, and then come out certain innovative experimental skill. And for that, initially, teachers are being trained how to do, and then some students are registered for that, few of them, and then they will be given scholarship for their higher studies. Another one is the national standard examination for schools as well as colleges. The winners of this examination at the national level, they have an advantage. They get scholarship along with the certificate. But SM Bose National Center for Basic Sciences, Kolkata, allows direct admission to national toppers of these exams after an interview in their integrated PhD program. So I expect probably PRL in another way may be able to think of many of these national toppers. If Kolkata Institute, Bose Institute can do it very well, probably PR can also think of. I'm not putting, it's just an extension and appeal. So national competition for innovative experiments is being now launched and its registration is going on. I hope many of the physics teachers, the physics research scholars, as well as junior scientists, they will be participating and encouraging these activities. Today, what we see largely is there is a tendency from the school to college level to avoid experiment. And that is creating a lot of problems in the basic understanding and maintaining the interest in physics. So our effort would be more to give stress towards training and showing the importance of experiments in physics. Without experiments, nothing can progress. At the same time, both theory and experiment should go hand in hand. Then only new physics or new knowledge can be generated. With this brief introduction, I stop here and I invite Professor Joshbira for introducing our worthy speaker of the 6th IAPT, PRL-IAPT Vikram Sarabhai lecture. Thank you.
Thank you so much. What a pleasure it is to introduce the invited speaker, Professor Nigel Mason, whom I have known for about 25 years now in our joint collaborations and publications. Professor Nigel Mason is the 21st century physicist who is going to talk to us about a very interesting and insightful topic today. Professor Nigel Mason, OBE, is a professor of molecular physics at the University of Kent in UK. He began his research career by exploring the processes of simultaneous absorption of energy from photons and electrons to excite an atom. It is a process akin to two-photon absorption, and it was predicted theoretically in the 1930s but not previously demonstrated experimentally until Professor Nigel's PhD studies and early postdoctoral studies 1984-87 in the Department of Physics and Astronomy, University College, London. He was awarded a Royal Society University Research Fellowship during 1990 to 98, which allowed him to form the Molecular Physics Group at the UCL. And then in 2002, he was appointed professor at the Open University, Milton Keynes, UK, where he was the Dean for the Research, Enterprise, and Scholarship in the Physical Sciences. In 2018, he was appointed head of the School of Physical Sciences at the University of Kent, UK. Since 2023, he has been a scientific advisor to Atom Key in Hungary, one of Europe's largest accelerator facilities. Professor Mason's research may be broadly classified as molecular physics, which encompasses several interdisciplinary themes: astrophysics, astrochemistry, environmental and atmospheric physics, plasma physics and nanolithography, and the next generation radiotherapy. However, all of this research is centered upon fundamental or foundational, shall I say, studies, and the subsequent reactivity that is about the topic, photon-induced fragmentation, as I was telling you. Nigel has over 420 referred publications with an H index over 50. His research has led Nigel to leadership roles, and I think this is very interesting, very important, something very special about his personality. Leadership roles in many national and international research programs, and he was the president of the Euro-Planet Society, Europe's largest forum for planetary sciences, and is the coordinator of Euro-Planet 2024 research infrastructure, providing access to data services, facilities, telescope networks to study planets, moons, comets, and asteroids in our system, our solar system, and beyond. Outside Europe, he has close links with the emerging space community and electron scattering community in India and electron physics communities around the world. He chairs the Dissociative Electron Attachment DEA Club. He also chairs the Sir John Mason Academic Trust, a small family trust established by him in honor of his father. His father was also a distinguished scientist and pioneer in the study of cloud physics, and Sir John Mason, his father, also visited PRL some years back. Friends, a scientist is a three-dimensional personality. A professor is a three-dimensional creature, let us say. The three dimensions of endeavor are teaching, research, public outreach. These are the three dimensions. And I'm very happy to say that Professor Nigel is indeed a learned three-dimensional personality, as he has very actively contributed in all these three directions, all these endeavors. Therefore, we greatly appreciate the theme which he has chosen for his lecture today. With these remarks, I invite and I request Professor Nigel Mason to deliver 6th PRL-IAPT Dr. Vikram Sarabhai lecture. Thank you.
Okay, can we remove the okay. Right. Yeah. Does it move? No. It did before. Yeah. Okay. Okay. Right. Okay. Okay. Well, while he's doing that, I might as well just say thank you very much for the invitation. I haven't got the microphone yet. It's over there. The first lesson is nobody falls asleep in my lectures. I was told this when I was lecturing in the top floor in UCL, and one of the professors 4 doors down said, I can hear you. I said, I don't believe you. And in the next lecture, he wrote down my lecture. So, golden rule number 1 for being a physics teacher is to keep your students awake. We have student appraisal. Last year, one of the students' appraisal was, I really enjoyed Professor Mason's lectures. They're the only ones I didn't fall asleep in. I don't know if that's the credit for the best lecturer, the only one that the students didn't fall asleep in. But probably because I'm too loud. But that partly goes for the fact that my father was a very famous scientist. He did come here and lecture at PRL. And when I first came here, there was a picture of him lecturing here. He also was very loud. So in our household, you can imagine that if we were having a discussion, I had to be louder than him. Right, are we there yet? Not yet. Okay. It's here, they're trying to get it on the online part, that's the point. Okay, we'll let them try. it is also very good to talk to physics teachers. As you heard, I did my first degree in physics at University College London. It's one of the most famous physics departments in the UK. But I have moved, and I gradually moved from physics towards chemistry and chose the title of Professor of Molecular Physics. That basically means that I felt I needed to study something other than hydrogen and helium and atoms, because most of the world is molecule. So I became a physical chemist, and I started to look at the ozone hole and that sort of thing. And then I moved into astrochemistry, and then I moved into radiation studies and everything else. So I started off in the physics department. I then moved into a department of physical chemistry. Then I moved into the physical sciences. And then I took over a department of physical chemistry where one of the largest areas was forensic science. And so, but now we've just had a restructure in the university. And now finally I'm back again in the Department of Physics. So it's really nice to talk to physicists. Now, are there any non-physicists in the room? Where are the chemists? Hands up if you are a chemist. Right? If you're a biologist. Right, you can leave. Right? This is the physicists, right? And what I'm going to talk to you about is being a physicist in the 21st century. And the very final slide is directed at all of you. It is a mission for you, okay? And that's when we ask the chemists and the biologists to leave. It's what physicists are going to do. Okay. The technology isn't quite working. I went to a lecture where the Molina, who won the Nobel Prize for the ozone hole, and he stood up here, and just before his talk, he decided to make a change. It crashed the entire system, okay? He had about 1,000 people in the audience, right? We didn't have online in those days. Well, what do you do under those circumstances? He gave the talk with no slides. Okay. So if else invented the web. We know what to do, right? Okay. So the topic, when I was asked to give this talk, and I great honor, thank you very much for asking me. I thought about if I have an audience of physics teachers, what should I tell them? And what I thought we should discuss is the role of the physicist and what the physicists can do for the world today. Because you are teaching a generation that is going to have to go out and face crisis. The world is not a happy place. Indeed, I would contend that my generation has had it easy. We've had probably the best times economically. We haven't had any wars, major wars anyway. We haven't had to face the real consequences of things like global warming. We've had COVID. We haven't had a nuclear war, but there are lots of problems coming. And our next generation is going to have to address those problems. And when I look at my daughter and I think of what she's going to have to cope with, it worries me. But how are we going to tackle these crises? Who is going to solve the crisis? Now, If you believe it's the politicians who are going to solve all the problems of the world, and you have faith in them, put up your hand. No one. All right. Well, I'll give you a second option, right? Go back 300, 400 years. If there's a crisis, there's only one other thing you can do. Pray. Right? Now, I would suggest that neither of those options are good options. Right? So, we have a third option. We have scientists, and we, yes, chemists and biologists, you're welcome here. Right? Right? We do science. And we can address our problems in a scientific way. And that is what I want to talk about. I want to talk about the challenges and then how physics tackles those problems. The sort of problems that the people you're teaching today will go into, hopefully, and to help to solve the problems that we will address as a world society. So if you ask what the big problems are for the world today, for the science today, let's just look at a few of them. The first one is health. Okay? My father died at 92. My mother died at 92. I hope this is a trend, right? That means I have a third of my life or more to go, right? But I want to be healthy during that period of time. What's going to get me, right? Well, cancer might get me because cancer gets a lot of us. You're going to suffer from it. Everybody in this room has probably known somebody who's got cancer, and they will have a family relation who will get cancer. We've got things like Alzheimer's and dementia, which is a terrible thing if you have family members who suffer from that, to watch them decline and to watch academic colleagues. Many of you may have academic colleagues who are suffering from it. So we need to think about how we can cure that. And that is not just a problem for medics. It's a lot of the technology and stuff is done by scientists, and a lot of it, as we'll see, is done by physicists. The next problem big problem is energy supply. We now really face this as a struggle. Everybody here has probably seen the prices of electricity go up, all right? I have debates. I'm away for 2 weeks. Should I leave the heating on for the cats? Right? Because would it be fair that I just switch it off and they're in the house for 2 weeks, nobody there, and they get cold? Well, of course, the answer is, of course, I'm English, so of course I leave the heating on for the cats, right? I have to work out how long to leave it on. But seriously, energy supply is going to be one of the critical issues. And what type of energy supply with global warming? Windmills? Yeah. I don't recommend UK going solar, right? It's not good, right? Solar is not good in Britain. Windmills, yes. What about fusion? Every time you talk to a fusion scientist, it is going to happen in 50 years. They said that in the 1950s, the 1960s, the 1970s, the 1980s. It's still 50 years. What about other ways of reducing stuff? What about the electric car? Anybody here got an electric car? Is there the Indian electric car yet? Yeah, right. Anyone got one? No. So you're all environmentally unfriendly people. But there's a problem with an electric car. It's called the battery. I work in Hungary, as was said. I work in the town, not the capital. It's Debrecen. Debrecen is about 170 kilometers from the capital. As you will all know, all politicians and all government meetings are held in the capital. So you have to go to Debrecen, right? If you drive to Debrecen in your electric car, you may not get back. There are not enough charging points in the capital, so you can run out of your battery before you get back. That's a problem on energy supply. And so we need people working on batteries. The global warming issue. Understanding global warming. making new plants for global warming. This is a science problem, a wide science problem, but it's also a problem which physicists are working on. I worked in the ozone hole, as I mentioned. You know, we have to save the penguins. And but again, although I was a physicist, the work that I did, and I went very quickly from being an electron collision physicist to doing photo studies and chemistry in the ozone hole, which is a surface chemistry problem, which then led on to the astrochemistry I talked about today. So before we talk about the physics, let's just talk about science in general, because it's important to get some numbers about science and scientists. Yes, we're physicists, we're chemists, we're biologists, we're mathematicians and everything else. But most of all, we're scientists. And scientists are the minority. Most people are not scientific. Most people are actually quite scared of science. So science is, however, expected to solve the problems. Government think that scientists can solve the problems. We, in turn, ask them to give us money, promising we will solve the problems. You've been investing in fusion for a government for 50 years, maybe you feel you haven't got a good amount of money. So, to tackle these issues, we need science. We need scientists. And I will claim, sorry, chemists and biologists, but most of all, we need physicists. However, an important fact, scientists are genuinely trusted. This is a report that came out a while ago, but I think it's very much the same in nearly all countries. It's how trustworthy the profession is. Scientists are top, right? 60% of people trust scientists. 9% trust politicians. That's probably 9% too high, to be honest, right? But look at the others. Scientists are higher than doctors. They're higher than teachers. But that's not just science teachers, you know. Proper science teachers, very high, right? Armed forces are 43%, police 38%. You just go down there, right? So this is a really important factor. And even here in India, I mean, my colleague sent me this during the COVID. This is some of the things that the governments all around the world were relying on. In the UK, the government was panicked. I mean, we're having a big review about it. But if you actually talk to people in government, they hadn't got a clue what was going on with COVID, because none of the politicians knew anything. And they were relying on, their big message was, we know you don't trust us, but we've got these scientists here, and we're doing what they tell us, and we know you trust them. It's interesting now to take that debate and think, has that, because they pushed the scientists front forward, there are a lot of people who still think some of the decisions weren't right, and therefore maybe the trust for the scientist is a little bit more messy than it was before, particularly in America. But okay, just a few other things before we get into about scientists in general. Why do scientists become scientists? And again, there have been several surveys about this. Okay. So they reflect on, they touch on multiple themes. Some, the curiosity about the world, the role of the people in their lives who fostered their interests. One scientist, I love puzzles. To me, science is the ultimate puzzle. I like the last one. Money is not the highest motivating factor, nor is making a difference to society. So we often hear that scientists, you know, okay, right, we're not poor, right? But we're not rich, right? What wasn't said, and normally was said when I come here, is, oh yes, and Nigel played for the England under-19 cricket team, and I played some guy called Ravi Shastri. I don't know what happened to him. He come back to India and did something. But I will guarantee that if I was playing cricket today and I was playing at that level, I would make a lot more money than I am now, right? If I was playing in the IPL, wow, right, you know, my helicopter would be out there waiting for me, right, you know, etc. I can get out for naught just as well as any of the England batsmen can, right? No problem. But it is these important things that scientists are driven by their lifelong learning and their curiosity. But what attracts them into science is also very early on who they meet. And That's where you come in. If you have a teenager, you will know that they will not listen to you as the parent. Forget that parents influence teenagers, right? If I say do that X, my daughter will do Y, right? Even if I say it's daylight, she will argue it is dark, right? So who does influence? One of the critical issues, and it's well known in the science, and it doesn't matter which country you're in, is the person who introduces them to science. And that's you guys. That's the teachers. And if you don't inspire them, who is going to inspire them? And I'll come back to that theme later. Now, let's talk about physicists and physics. Now, first of all, physics is perhaps the oldest science. If you think that science began by people looking up in the sky and thinking about astronomy and when the seasons were and when you should plant something, etc., then we're definitely the oldest science. Physics is the oldest science. So the question you have to ask yourself, oops, go back, is what springs to mind when you think about physics? Okay, what do you think about? What is physics? How do you think of physics? How do you describe to somebody? You're at your New Year's Eve party, right? And everybody's sitting around there and they're talking about what they do, and you've gone with your partner or whatever, and your partner's got to introduce you, right? And they say, yeah, well, physicist, a scientist, oh, boring. Let's go and talk to somebody else, right? But what do you think about physics? How would you introduce yourself? How do you describe yourself as a physicist? And how would you define the type of people that you work with? What is people in the room here, how would you describe yourself as a collective? Because you are a group of people, you're a physicist. What is a physicist? And then, do you think of your future? You will, because you're teaching it. But asking students, asking people studying physics, is physics, they might study physics at university and so on, or at school, but how do they think that physics is going to go on for the next 70 or 80 years of their lives? And then what jobs do physicists do and what qualifications do they need to get? These are the questions that we need to ask. So let's think of physics as a career, okay? I would claim that physics opens doors to some of the most exciting and cutting-edge, rewarding jobs in the world. If you ask people about rewards, and are you happy with your job, right? Scientists on the whole say yes. People working in a supermarket say no. People working in the civil service normally say no. Doctors say yes and no because they feel rewarding, but they feel the strain. What do physics teachers think? In Britain, a physics teacher will say, I really enjoy teaching to the students, but I spend 70% of my time filling in forms, doing bureaucracy, and trying to follow new government initiatives. And I hate it. All right? They will also say, I also hate having to try and control the class because we have issues, particularly at school level, on discipline and attention, and particularly for students of today. Nonetheless, scientists. Now, amongst scientists in the Institute of Physics survey, it might be biased, but when they asked teachers and they asked people from the different disciplines, physics, chemistry, biology, physicists said they were the happiest. Okay? So I hope you're all happy, yeah? But a really happy group of people in here, yeah? You're all great, you're all feeling good, it's the beginning of the year, you can't wait to get back to teaching and doing your stuff. Okay. But the physicists' reason for being happy is that they are inquiring people, but they also do feel that the questions that they're doing have some relevance. So from cancer treatment, climate change, gaming, robotics, artificial intelligence, physicists are on the front line. They also hope to shape the future. So physics opens these doors because it provides you with a set of skills and a way of thinking. And that is what defines you from most of the rest of the world. That you think differently. Now, in the UK, 1 in 20 jobs, 1.85 million jobs in the UK and Ireland make use of physics. So 5% of the employable people will use in some way physics. That's a lot if you think about it. So why are physicists so interesting? What is it that they've got? And what makes employers like physicists? It's because we have certain skills. Physicists are believed to be mathematical, they're analytical. There is a very strong correlation between physicists and things like doing crossword quizzes, Sudoku. There's also actually a very strong link between mathematics and physics and music. A lot of the people, quite famous people, physicists, have also been very good musicians. But a good physicist isn't just an encyclopedia or Wikipedia. They have developed critical and creative thinking skills because they solve problems. And that is what physicists should be trained to do. They shouldn't just be people who regurgitate facts, they should be able to think about problems. So which of these skills do you think you gain from doing physics? Problem solving, experimentation, creativity, data analysis, digital skills. But what about presenting skills? What about communication, writing skills, teamwork, decision-making? Are those skills for physicists? Absolutely. We cannot do, particularly in research, modern research, without any of those skills. Your teachers, you are like, you go in there, you're a salesperson. You're selling your stuff to your school teachers, your children, your college students, your undergraduates. They want to be entertained. And we're with the TikTok generation. Can anybody tell me what, according to educationalists, is the attention span now for your average undergraduate student? How many minutes? 20 minutes. 20 minutes. 20 minutes I have. Any others? 7 minutes. You're the closest. It's 8 minutes. The attention span of undergraduate students in the UK and in America and in Europe is about 8 minutes. That is why when we had COVID and we had to teach from home, you cannot give your undergraduate class a 40-minute, no gaps lecture. There won't be anybody left at the end. Right? So we taught in 8-minute segments. You teach for 8 minutes, then you give them an exercise to do. You know they're alive. You know they're there. My daughter, 17 and a half, I don't think her attention span is as long as 8 minutes. Okay? You have to keep their attention, which means you have to constantly give them things that are going to make them excited and enthusiastic in your teaching. So these are some of the skills that we look for physics graduates on CVs. You've got the basic skills here, some of the things we might expect them to have gained after doing a course. Look at the computer programming now, very important. I did Fortran 77, God help me. The days of computer, that was the last year of computer cards. Does anybody here remember the punched cards? I think, yeah. God, it was hopeless. Then we moved into C++. Now we teach in Python. Python is the language now. You cannot send a student out of university at a physics degree without that. And maybe MATLAB. But we do have to make these other things as well. This is what you have courses on. You will teach them quantum mechanics, thermodynamics, electromagnetism, classical mechanics, statistical, probably astrophysics, nuclear physics, particle physics, condensed matter optics. These are all the things you will teach them, right? But you also have to teach them the modeling, the data analysis, laboratory techniques, how to design experiments, how to write things, critical thinking. These are the other skills that you need to teach them to be a professional physicist, a person who's got on their qualification, I'm a physicist. So what do physicists do? This is Bell Labs. Most people will know Bell Labs, the chief technology officer, many of them in companies. Many of the companies end up with physicists running them, okay? And this is universal. It's in China, it's in America, it's in Europe. We find that physicists often end up in administration and leadership positions. And the head of this lab said the most desirable employees in industries are physics undergraduates with a master's or a PhD in engineering. National policy. Physicists lead all scientists in the contribution to the national policy in many national and international issues. Albert Einstein, Richard Feynman, Carl Sagan, etc. In an increasing technology society, physics gives best training for global interdisciplinary perspective. For example, quantum computers have been predominantly led by physics industry. These are the sort of jobs you will get. You will probably tell your students these jobs. There is the research assistant. There is the person who stays in to do research. Okay. Further physics-based research or STEM in general. These positions may involve assisting with experiments, collecting data, analyzing results. There's the technical writer, because physicists should have the technical skills. If they go into industry, they're expected to write reports. Our undergraduates and postgraduates complain about writing reports. Wait till they get to industry. Every month, they've got to write a report. Software engineering. Very strong number of physics graduates go into software engineering, particularly in the space sector. Nothing works in the space sector without good computer code. You can't go up there and fix it when it's at Mars. So you have a lot of that. A lot of data analysis, a lot of data techniques. Then you get people who go into science education. That's not just teachers. It depends how you define a teacher. As was defined here correctly, teaching starts at school, it finishes at university. So teaching should be thought about across the board. I have been head of department, I've been dean, I run international panels. But my principal focus when I became head of department was always, and I was told, oh, you don't have to teach. I said, well, I'm sorry. I'm not going to send my guys out there to teach if I don't do the teaching. So in this term, I teach 3 courses. I actually teach 3 courses concurrently because we're short of staff, which means in one case, I will teach atomic and molecular physics, and then the class will follow me like the Pied Piper across the campus to their next lecture, which will be on space physics. But I think that's important. I don't want to forget the teaching. And if I can keep the students awake, maybe that's useful. But there are other jobs you may not have thought about. Patent attorneys. A lot of physics graduates are actually the people, when you apply for a patent, often the person reviewing your work in science is a physicist. Engineers, lots of things, particularly in aerospace and so on. A lot of physicists become engineers. I will talk more about being a medical physicist because that brings you into the whole aspect of the health industry. Medical physicists are really vital for that. But also, we need to communicate. We vitally need to communicate what science we do. And therefore, the communication, physicists again go into that. And several of my students, interestingly, all of them are female, have gone into the media, the BBC, local news radio, news scientists, etc. They've gone into those jobs. 55% of physics graduates in the UK find employment in a physics-related job within 6 months. That's a very good statistic to tell parents. Right? And they usually go into research and development. 12% of physics bachelor degrees find employment in other fields, including finance or engineering. 40% of physics bachelor students in America go on to do a higher degree. That's either a master's degree or something else. And this is just some figures from America that show that. I won't go through it. These are just some of the employments in America, just listing some of the places that they went to from Harvard, etc. You can just see it's pretty much the same. All right, so I'm now going to give you a few examples of physics in action. Okay? Now, none of these, I think, you will think is physics until I tell you it was all done by physicists. Right. Number 1, jellyfish lasers. Let's make a laser out of a jellyfish. Bioluminescence is the process that enables the fireflies to glow and jellyfish get their glow. Okay. The crystal jelly was found off the west coast of America. It uses a protein to produce bioluminescence light. Physicists have extracted that protein worked with biologists to grow it in E. coli, created a film 1,000 times thinner than a human hair, put it between mirrors, shine light on it, and hey presto, they made a laser, a biological laser. Okay. They can operate at room temperature. Okay. And this is now thought to be many ideas. It's very cheap to make this stuff. So physicists working with biologists, getting the idea that we can use these proteins to produce something which is a laser, which most people will say is one of the big discoveries of physics. The guy who said that physicists are good at being leading things, this is this chap, executive vice president of a big data center in Phoenix, Arizona. He did his degree in physics. What did he work on? He worked on with Lockheed Martin. He worked on how to design the wing shape of planes. You now see at the end of the planes, you know they turn up at the end, right? They're not flat, that little bit that goes up at the end. That's because it was physicists worked out by first of all doing models and then using wind tunnels that this would help with the drag. So this is physics, engineering together. Okay. Understanding the physics principles, the people who did it were in the physics department. What about other things outside this world? Okay. All the things about exploring the world beyond. We talked about that all in the meetings today. Okay. But to go there, we have to build electronic devices. All those lovely pictures you see from JWST and everywhere else, they rely on the development of the camera that did it and the semiconductor and the technology that gone beyond that. That is a big area, and it came again predominantly from physics department. NASA is working on making circuits from silicon carbide, and if you don't make it to make a silicon chip, you can make it as a bulletproof jacket. It's materials science, but with the understanding of physics. So I thought I would tell you what a physicist does every day. Okay? Now, there is no personal slant to this. Okay. Of course there is. But I'd like you to just think when you're talking to your students and explain to them how every step of their day is determined by physics. So let's start by waking up. You set your alarm clock, yeah? Your alarm clock, like all clocks, is synchronized to the atomic clock now. The definition of time is by an atomic clock, which are much more precise than conventional, and they have a much higher frequency. That is done by fundamental atomic physicists working out transitions, good old-fashioned spectroscopy, etc., but using it. Okay? And you've got to think of that, we're putting atomic clocks in space, etc. as well. So atomic clocks are based on cesium atoms. The second has been defined now as the duration of, you can see the number there, for the transition between the cesium atom. And the cesium clock is accurate to 1 second in 316,000 years. All right? So when your students are late, explain to them that they have no reason for being late because the clock that woke them up is they can only be wrong by 1 second in 316,000 years. So if they tell you their clock was wrong, they're lying. Right, now let's go to breakfast, okay? So, what do we do for breakfast? Now this is I know Indian breakfasts are different from maybe European breakfasts, but we will have porridge. And so we will use the microwave. Teenagers love microwaves, by the way. Cooking is not, everything is done very quickly. Anything that can go into a microwave for 60 seconds is brilliant. So, but explain to them about a microwave. A microwave works on the principle that the food contains water, and you heat the water up through the oscillation of that. That again was designed by people in a physics department. Indeed, many of the people who did it were working on microwaves for astronomy. When they first brought it out and they had the microwaves, they had Jodrell Bank, which is the big radio telescope in Britain, they had problems because they got some kind of strange signal that came between 6 and 7 o'clock every evening. Because people went home and switched the microwave on and they saw that with the radio telescope. And they had to put filters in to get rid of it. So while you're doing that, you're going to switch the radio on or the television on, and you're going to do radio transmission. And that's all physics. That we understand this from the 1920s and the 1930s, the idea of how we transmit signals, radio signals around. We bounce them off the ionosphere. And PRL, great place for understanding that. Okay? You might be lucky. We are in a period at the moment where we have a very active solar wind. So we can actually see aurora in the south of England, which is very, very unusual, okay? Because it's so active, okay? And this is, again, understanding this is understanding collision physics. That's what my PhD was supposed to be on. I was supposed to do experiments on electrons interacting with oxygen. Unfortunately, my supervisor hadn't got a clue what he was doing, and he set me a problem which was never going to work. So while he was away in the summer, I decided to do another project, and I ended up doing this electron photon excitation. Okay, let's turn on the TV, right? While we're having our breakfast, you've got the remote, you press a button, you get a connection. Wow, but you're using infrared light. I'm using it now, right? The clicker, right? Okay, again, that's physics. Right? And this was also developed in the physics department in a month. Right, so we've had breakfast, we're off to work. So we get in the car, right? Now, this is obviously an English one, because in India, you don't need sat nav, right? Because you just have to follow everybody else, I guess. But you know about GPS, right? Now, my daughter's 17 and a half. She's determined that she wants to drive. A horrific prospect for the person whose attention span is less than 8 seconds, right? And what car should I make her drive? Should she drive an electric car? Should she drive a diesel car? If she drives a diesel car, maybe she'll have the skills to drive an electric car. I suspect that if she drives an electric car, she won't have the skills to drive other cars. She also hasn't quite worked out the driving's the easy bit, the buying the car is the expensive bit. And the insurance on the car is even higher than the damn price of the car. Nonetheless, she wouldn't know where. Her sense of direction is 0. She gets lost going to the bathroom. So the chances of her getting anywhere without GPS are minimal. So GPS, this all again came from people working in physics departments with their engineers. On the way to work, I pop into my local company because we're working on manufacturing and silicon chips. You all know this is the huge area. This is where everything. I was in Taiwan with Bala before Christmas. 1/3 of all the silicon chips in the world are made in Taiwan, and nearly all of them are made in the city we were at. 8 factories were making silicon chips there. Each factory's production area was the size of a football pitch. So, but making those chips, making them smaller and smaller so that you can get more and more information on them, so your phone can do more and more things, etc., requires an understanding of a lot of physics, and particularly plasma etching. Now, unfortunately, maybe one of your relatives is a bit ill and maybe they need some cancer treatment. We'll come back to that for a moment. So you might pop into hospital, see your grandmother on the way to work or whatever, and she may be having some radiation treatment. We'll see in a moment why that's physics. Because radiation damage at the molecular level is one of the breakthroughs of this century. Up until now, radiation physics, radiation therapy was a little bit of a black art, okay? We now understand much more about how radiation interacts with the cell and breaks up the DNA. And we can come up with new methodologies. The next slide does it. Yeah. The new methodologies is to use ion beams to focus, to use ion beams. So you fire an ion beam which targets the cells, the tumor. You don't irradiate all the good, healthy tissue, you irradiate only where the cancer tissue is. Okay, so you can do high dose, but in a very confined space. And this hopefully is more effective at killing the tumor, but on top of that, it spares all the nasty side effects you normally get. And there are certain organs where you really want to do that. You do not want to irradiate the entire brain for a brain tumor and kill much of the good stuff. You want to target the cell. But to understand that, the physicists had to explain how the individual ions interacting with the individual molecules within the DNA and how that would be done. And that's led us to produce new drugs, new nanoparticles, which we could put into the cells which also interact more strongly with the radiation in a different way. So we used to say that, atomic and molecular physics, well, if you got some of the numbers wrong, you wouldn't kill anybody. Unfortunately, the answer is now you will, because if the data is not good enough, you may give the patient too much radiation or too little radiation. So we really do need to have this foundation physics well understood before we let loose on patient. Okay, now we're going to go to lunch about food chemistry, okay? Well, yeah, food and chemistry likes to go together, but a lot of it is soft matter physics. The design of ice cream, which I adore, as Bala knows, right? That designing types of ice cream was actually developed in Unilever by the physics division because they were soft colloidal chemists, but they were also physicists, soft chemistry physicists. Okay? Okay, so after that, I go into the lab, and it's a bit of a hot day, so I turn the air conditioning on. And this means the physicist has got to be thinking about global warming and the problems of global warming. And to understand, first of all, global warming, the underpinning science, what's it all about? It's about radiation being trapped in the atmosphere. So you can't understand that if you don't know how the radiation is absorbed by the molecules in the atmosphere and then they're re-emitted to the ground, and this produces the global warming. So you need our glorious spectroscopy friends down here, because if they do not get this right, all the predictions, it mustn't be more than 1.5 degrees. How do you know that? It's because you've built a model, and in that model, you've put some molecules in, and you put some concentrations in, and you've put some cross-sections in to determine these numbers. But you also need to understand cloud physics. My father was the first professor in the world of cloud physics. And he wrote the book. It's called Physics of Clouds. And there's even an equation. He has an equation named after him. You can look after it. It's called the Mason equation. I think that's great, to have an equation named after it, right? And it's about how ice crystals form in a cloud. But the type of ice crystal you have in the cloud, and there are lots of different types of snowflake, determine the reflective properties of the cloud, which in turn determine the radiation budget, which is very critical. So if you have global warming, you get lots more water, you get clouds. Clouds can be good and they can be bad. Some clouds just reflect the light back from the atmosphere back out to space. Some absorb the light coming up from the Earth and therefore trap the heat. And the same thing goes for aerosols. I flew into Delhi. Yeah, it was rather foggy. That was not natural fog, right? So we need to understand that. And that means we need to understand thermodynamics. But also, the scientists and the physicists have to think about, okay, realistically, whatever people say, 28, whatever, it looks like we've blown it. We're not going to keep it down as we think. It's going to get hotter, and nobody is going to really address the issue sufficiently because no politician, no government, and basically most people are not going to take the pain. So the only thing we can do is start to think about ways of mitigating it. And that means we have to give people options. So we have to do the wind power. We have to do the solar power. We have to build electric cars to get rid of petrol engines. All of that requires a fundamental understanding of a lot of the physics principles. We also like to know where we came from, where we're going, what's out there. All the universe, all the studies we've had, in people who weren't here from the teachers, but we've had today's meeting and tomorrow's meeting is about astrochemistry, astrobiology, understanding our role in the universe. That's what a lot of physicists really like to do. Not just physicists, we have chemists, we have biologists as well, because we're working coherently. But it's a good area. We produce mimics of new worlds. Somebody gave a talk earlier was mentioning Titan reactors. This is our Titan reactor. We like Titan. We like to make the dust of Titan. But this is a physics thing. It's about plasma. It's about mimicking stuff. It's understanding the properties of these things and the energies that go into it. We also have the whole world of nanotechnology, making things very small. We talked about the silicon chips, but we can build things on a very small scale now. Here are some of the structures that we build. These are just things saying the size of them. There's your buckyball, which we've been talking about. This is a 200 nanometer buckyball made from carbon, but in the shape of a buckyball, right? We can make structures. We do this by interacting electrons and gases on a surface. something which people here in India, particularly my colleagues here, Joshipur, Chetan, and Nashki, and so on, they do calculations for these molecules. I just saw, shouldn't say this, but I saw a paper of theirs recently, which I got from FOE. It was really good stuff because they really tackled this problem the first time. Okay, I'll finish my work for the day. I'm now going home, but I probably, a bit fatter than I need to be. So I go to get a bit of exercise. What about playing a bit of tennis or badminton, I guess, if you're here in India, or just go for a run, okay? But the design of the tennis racket, the materials in the tennis racket, you've seen it. Tennis players today are serving much faster because of the materials that they do. That comes from materials physics. The chemistry and the design of that comes from physicists. And indeed, again, the running shoes. So these are the materials we use for sport. Okay, there's a lot of nanostructure going into that. So I go home. Okay, it's the winter. I turn my lights on. So what about all the lighting? The most energy use in the world is actually one of the biggest users of energy is the lighting. All those neon signs you have everywhere, really bad. So can we make these more efficient? Can we make lighting so that it's much less energy consuming? And the answer is yes. We can build new types of fluorescent light sources if we can understand the interactions of photons, electrons, and fluorescent material, like those bioluminescence type things. I turn on some music, I put my CD in, I've got my laser again. I've got my laser everywhere. Okay? And using the laser, again, a classic example of physics. And somebody said earlier today, when the laser was invented, people say, oh yeah, they're both nice. Who's ever going to use it? That was one of the worst predictions in history, was that there'll be no use for a laser. Right? That almost ranked with when Faraday was doing demonstrations on electricity, and the treasurer of the UK, the finance minister, said, "Oh, that's very interesting, but is it any use?" To which he replied, "I don't know if it's used now, minister, but when we find one, you'll tax it." He was correct. So you know about how lasers work, stimulated emission of lasers. Okay, so I've had my hard day being a physicist. I go to bed and I go to sleep. And that's my day. So I hope that's given you a picture. And I think it's really nice to tell students that. I use this talk quite a lot when I go to school, explaining why physics is important to them in their everyday life. Right? Everything they do. And I can do it for science as well. And I can bring chemistry in and biology in as well. And I do that one as well. But the world uses physics every day. You use the results of physicists every day. Physics is therefore core to what we do. So I claim that physics and physicists are going to be key to addressing the great challenges we face today. If the physics community, the people you train to be physicists, are not enough of them and they're not there to do this, we will face a crisis. Because the use of physics, the knowledge of physics, the application of physics is going to be vital in answering some of these problems. And that's why teaching physics and getting people to be physicists is so important. So the world needs physicists. Okay? Are you all going to agree with that? Even the chemists? Right. Now, I need a takeaway message, don't I? Right. The scientific community. STEM researchers are 0.1% of the global population. 0.1% of the world's population are scientists, right? That means there are 8.8 million scientists worldwide. 88.8% of those 8.8 million scientists are in the G20 countries, right? 93% of the research spending and 90.1% of science publications come from 20 countries. Large parts of the world, therefore, don't have scientists. And that is a really big problem. So if you are a scientist, if you're a physicist in the G20, as you are, I think you have a duty to support colleagues outside your country. Look at your boundaries. How many physicists are there in Nepal, in Myanmar, in Laos, in Indonesia, who are going to face some of the biggest problems of climate change? Have they got resources, skills, networks to teach their generation? Can you help? Okay. What's the best age to attract students? Before 10, between 5 and 10. Who thinks it's before 10? Who thinks it's between 5 and 10? Who thinks it's after 10? Yeah, most of you are just not committal. All right. Well, the best age is believed to be before 10. That's what what a lot of the surveys in Europe show. If you do not attract people and they do not feel that science is for them before they're 10, it gets increasingly hard to attract them. You'll only get the ones who are small minorities. If you want to get larger numbers, you've got to get them early. And who influences them the most? The teachers influence them the most. So I would claim that although we do an awful lot of work with teachers from 12 to 15 and then 15 to 18, what you really need to do is get the science teaching into the preschool. Because those teachers don't do science. They're scared of science. They have to teach maths. Well, science is the thing they fear. They don't feel that they can teach it. If they teach it badly, that their students are not going to think about doing science when they become more than 10. So I don't know what your age group is for your physics teachers. There aren't such a thing as physics teachers pre-10. They're just science teachers. But I think we need, like in England, we need to get to those people. We need to get to what we call the classroom assistant. Because in England, there's a teacher and then they have 2 classroom assistants. Who the classroom assistants don't get any training. On their teacher training courses, they don't get trained science. We're arguing that's got to be compulsory now in their training. Of course, to get the qualification, they've got to get some hours of science in their training to teach children under 10. So, the final message to all of you. The future of the world and the human race lies in your hands. Now, I was going to have a nice picture here, one of those famous "the world needs you" pictures, right? But unfortunately, due to the fact that PRL doesn't let you onto the internet, I didn't add it, I couldn't get it. But I am serious about that. I don't think there can be any more important message in teaching at the moment, but to say that we have to get science teaching for the next generation students right. They need to understand science. They need to know bad science. They need to know all the things that they get, all the lies or all the misinformation they get. They need to understand that they are living in a scientific world, that science is something they need to embrace, and that they need to encourage their children, if they're not scientists themselves, to think about science as a career. Okay? So I know, I've talked to one of my friends, she's from Bangladesh, and it's kind of like grandma says, oh, you don't want your child to do science, there's no money in that. Can't they be a lawyer or a doctor or even worse, a politician, right? No, we want them to be scientists. And I will claim that physics is that core. You have, a lot of other things are based around physics. Yes, of course, chemistry is good, it's great. Biology, really important. Medicine, really important. Engineering, really important. But a lot of the basic science, the fundamental, the foundations of a scientific career and a scientific knowledge, everything from wiring a plug, right, which is actually quite an important skill, right? A lot of people around the world die by electrocuting themselves because they don't understand electricity. That's physics, okay? It goes back to Faraday. You are the teacher. You have the most important job. So when you go in to your class, tomorrow or whenever next, think about that you make a difference. If you get it right, we possibly have a chance in the world to get our questions right. But if you as teachers don't get the students to understand that science and even more become physicists, then we have a problem. So, it's up to you guys. On that note, I shall stop.
Thank you, Professor Nigel, for very exciting presentations. Now it is open for questions, discussions, and comments.
Very interesting lecture. In one of your slides, you said that the motivation to do the take the physics is not the make a change in society. Is motivation to do the physics or take a career in physics is not the making changes into the society. But
It's
most
interesting because when that survey came out, I kind of thought it's strange. Yeah, because I thought particularly the generation Z, right, is
Yeah.
supposed to be very, very environmentally conscious and wants to save the world. So I went into my lectures and I asked them what motivated them, why they were doing physics. And not a single member of the class said they wanted to save the world. What did you do to address that? They wanted to do, they were fascinated by astronomy, or they wanted to do research, or they wanted to make something, they would design something, etc. But all of that was about creativity, none of them said that, none of them, and then the same thing when you ask them, what are you going to do about money? And it's not true that physicists aren't badly paid. They are actually quite well paid. In the UK, the physicist's salary is pretty good. The average, I've got the figures exactly, but the average graduate, postgraduate will go and will be earning about 45,000 a year, which is, when the national income is about 27,000, you start from about 40,000. That's not bad for PhD. For undergraduate, direct practical students, it's still more than most people graduate, unless you're a lawyer or a The best thing, of course, to be in the vet. Right? The vet is the best paid in the country.
Yeah, so my question is still not over. So the physicists or scientists don't choose the career to make the change in society. They choose it because they're curious. Society or the government wants to spend the money to solve the problem and not to kind of just for the sake of curiosity. And the problem is more severe into the countries with less economic development. So where is the solution lies?
I spend a lot of time talking to politicians. In the last year, I had 4 prime ministers, right? And it was not a good time. The politician, you have to explain to the politician what science can do and what science can't. Okay? And they'll say these things because they think that's what they should say. You've then got to explain to them the real situation. Okay? And they will get it. In fact, look at what we're talking about civil service. In England, not 70% of the civil service comes from the pipeline. We're not telling you. But we have that debate now. It's I think it is becoming a crisis where there's been one country said it, every other country. So America said we're going to do quantum computing. Everybody else in the world. Then suddenly the Indians will say, what, really quantum computing? Don't we? So we have to have a sentence in quantum computing. Right? And we had a discussion this morning. It's about the idea of a fact. Something becomes factual. But it's responsibility also of the scientific community to explain that science does not go. You just don't suddenly apply something. You've got an awful lot of background stuff you need to have underneath it. And in fact, I think worldwide, that's the stuff that we're having. It's a classic in astronomy. Everybody wants to build really nice apparatus, send it up there and get data, but there's nobody actually producing the data to interpret the results, because that's fundamental science apply. So that's why we were discussing and calling it foundation science. Because I like the picture I had last night when we were discussing this, was this idea of having a house on sand, having your factory on sand, basically sinking, because there's none of the bottom stuff there. Nobody's doing the basic stuff on which everything else builds. And that's the message I think we need to get across. And maybe not use the word fundamental, because politicians think fundamental are people who want to write a quark, gluon, plasmist, which really don't have an industrial application. But both sides have very good application, but only if it's based on the physics, chemistry, biological principles we have to investigate.
Oh, thanks, Nigel, for a really interesting talk. In fact, I have given talks like this, being a physical chemist, chemical physicist. I agree with every statement you made. But one thing I have realized, Nigel, let me quote you Einstein. He said E equal to mc square. I studied physics as study of energy and chemistry as study of matter. Einstein said physics is equal to chemistry. And he said E equal to mc square. But anyway, that's a different matter. The question I wanted to ask you, as scientist, and of course, chemical physics, physical chemistry, I have agreed with every statement you made. But one thing I have recently realized is that, as you pointed out, 99.99% are not scientists. It's only 0.01%. And they need an earth to stand. They are not comfortable realizing that we are really hanging, not standing. I don't know if religion would help, but the faith is very important for them. Even though I don't know if I'm an atheist or agnostic. I fully agree with you when you say that we should not depend on politicians or God, because the reason I give to my students is that you've been given a hand and leg. If you have a problem, you solve it. But for a vast majority of population, almost 100%, this doesn't seem to work. How do we handle this?
Well, again, I think it actually does come back to what and how they learn in school. Because the only way you're going to get people to think about scientifically and think about science is when everybody does it. And the only place everybody does it is when they go to school. And again, this comes back to when do you do it? You do it before 10. You have to do it early. Because otherwise, and there is a duty, and this is something else which is really important, which Jakor said, oh, Nigel does the 3 legs and he does the public outreach. But it is important. Scientists can't shut themselves away and say it's somebody else's job to give a communication. It's somebody else's job to explain why science is interesting. I can't do that. I'm just going to sit in my office and calculate electric fusion cross sections or something. And so when you talked about the 3 legs, 3 dimensions, this is actually vital. And it's not just for physicists, it's for all scientists. But then I would urge, looking at some of the managing directors here, you need to recognize that too. The head of your college, the head of the school, the head of the university, the director of study needs to plan for the fact that his staff, his or her staff, need to do that as part of their job. And they need to have time to do that part of the job. And that's part of their duty. The university has a duty to educate the public. The schools have a duty to educate the parents. So put things on like, competition, etc., science competition, then invite the parents in. And so that they learn something about what their children are doing. And if their children get a prize, even better, they'll be more interested in it. But we all have a duty to do that, that 3rd leg. So when I was head of department, we have promotion criteria. I insisted one of the promotion criteria was if somebody had been really good in public engagement, science awards and so on, that was a period of getting them promoted. It wasn't just the number of papers they could do. Because actually, if they get a 30-minute TV series, they probably got more impact than publishing their paper inventions. And so I said, if they've done that, I'll promote them. And that's what we do. We have different ways of promoting. So that's how you have to do it. But where do you do it? I think it has to be at school because that's where everybody goes.
So now, okay. So now we have our national president IAPT online. He put his comment, some comment, and then we'll come back to you.
Sure.
Professor Anubhalia, sir.
Yeah, please.
Professor Nigel is here.
Yes, yes. Thank
for
you very
your,
much for giving me
comments and,
opportunity. Yeah.
interacting
Mr.
with you.
Nigel, I would
Please.
love to see you near the mic so that I may see you. Welcome to India. And I really enjoyed your lecture. I would say that it's a very, very timely lecture for us in India. The reason is that we are going through of new education policy and we are doing implementation. And what we are feeling is that the students opting for physics, their number is actually coming down. As a APT, body physics teachers, we are very much worried about it. I don't know whether this is the kind of trend in the rest of the world also, but what we are seeing is slightly worrying. This is one point which I wanted to make. But thanks to our founders of the country, particularly immediately after independence, we had a group of dedicated scientists and politicians who came together to raise the culture of what we call scientific temper in the country. And I think this lab where this lecture is being conducted, that is a kind of a witness to that situation. What I have to that how we can really make teachers, respondent to the needs of the society, because I think they are very much important into it. If they come up and raise their spirit to work in this direction, I think that will be wonderful. I would like to have your comments on that. The physics community through IAPT, 10,000 members, is doing a lot of work in that direction, but we still feel that we need to really work more so this situation. Thank you.
Thank you. Unfortunately, you were breaking up a little bit, but you started off by saying that the number of students studying physics is decreasing. And you're not alone. This is a trend across most of the world. In the UK, the students doing physics and chemistry was declining quite a lot. We've got the first evidence that's starting to pick up. That may be because people have seen there's been a lot of publicity about science and engagement with science with COVID and everything else. And so we are getting a small increase. But you started by saying there are 10,000 physics teachers. That's about 10 times what we have in the UK. 10,000, by any means, that is a big number. You should be able to make a difference in your country if there are 10,000 of you, okay? So I think the way there has to be a strong message, and there has to be a concerted policy of trying to get the message over to students. And that does mean addressing issues about teaching. Every country will have a different issue, okay? Every country will have a different issue. In the UK, the biggest problem is actually finding physics teachers, people who want to do physics, because most of the graduates don't want to go into teaching, okay? Because they hear bad things about it. They hear, what I told you, teachers like teaching the physics. They don't like doing the administration. They don't like the problems in the discipline in school. That's their front of. So if you want to know where a lot of the physics teachers go, graduate, the private schools where they don't have those problems, and they're better funded. Salaries are important. The salary of a teacher. Now, my family dates back. We were sort of classic agricultural family. The first son owned the estate and took it over. The second son became either an MP, because they had what they called rotten targets, basically you had elections, or they became a member of the church. The third member joined the Navy, and the fourth person joined the Army, and they probably came to India and places like that. And the women all got married off to the other local family. My father was the first generation who became a college. But he would always say that he grew up in the village. The respect was the landowner, the churchman, and the school teacher. And I will tell you now, I think very few school teachers in Britain feel that they have any respect. They don't feel that society respects them. And that's the issue that we have to address. And that's the issue we have to explain to politicians. That all this other stuff fails in significance. And they talk about, oh yes, we really value teachers. won't prove it. Make sure the career prospects are actually attractive to the people who want to get in. And that's where you need to have to go. But then applications will be different in Poland. In Poland, they had a very high degree of people doing science and engineering until the end of communism. Communist states had a lot of people going into science. It was very much encouraged. Then when communism ended, they had this big capitalist revolution. Everybody wanted to make money. And they didn't see science being a way of making money. They wanted to go into the civil service, they wanted to go and set up companies, and they wanted to do stock market. Now that's changing. Now gradually it's sort of come back. But for many years, their numbers just collapsed because it wasn't seen to be a career option they wanted. In America, it's very different state to state overall, and they have a very strange education system. So I don't know what it's like in India, but I think the most important thing is first of all, the teaching community has to work very hard and see very slowly. But if you don't do it, we're all stuck. Bottom line, we're all problematic. We're all difficult. But equally, that's where the argument has to come with the authorities about why the role of discipline. And I would argue that the English view at the moment is too much bureaucracy. And it's the same in the health sector. Why are we losing all our nurses? Not because they don't want to be nurses, because they spend most of their time filling in forms. The police spend 4 hours for filling in a form for every arrest. They don't make arrests because they're going to spend all that time. But the bureaucracy. And who runs the bureaucracy? Civil servants of the government. That's where we have to have the discussion. We have to get teachers being seen to be able to get on with it. But they then in turn take the responsibility for saying that I'm a teacher, I have a responsibility beyond teaching in my university or my college to others. And I say I think we need to focus most on the preschool. That's where we need to get it right. And I think that's the same everywhere in the world.
Okay, sir, thank you for joining us.
Thank you very much. Thanks.
Good.
Okay, here. Sure. Thanks for giving the opportunity. Professor Nigel, it was a fantastic talk, but I'm equally confused towards the end of it because you said everything is physics.
No.
I was told chemistry was one of the best topic, and therefore I did PhD in chemistry and became faculty in chemistry. And there is a journal which is called Small with a very high impact factor. And people publish papers on materials chemistry. And you said materials physics. And is it materials chemistry or materials physics, or it is materialistic? And towards the end of the day, you also said aerosols also from the physics. I do atmospheric chemistry. I'm really confused, Professor. Could you please solve my problem?
Well, when I gave a talk this morning, I was talking about interdisciplinarity. And I said one of the biggest challenges for people in disciplinarity is how we do like to sit in our silence. We like to declare ourselves a physicist or a chemist or a biologist. And actually, if we really want to go ahead, we actually need to break down those boundaries. So I can joke about my chemistry problems to say, chemistry doesn't want physics, just police and physics, the other things again, still quantum mechanics. But in reality, we talk about science. But we have to face the reality that when we come to teach it, that although we teach science in general, you have to get over the idea that there are disciplines, so we're never going to get rid of those disciplines. So absolutely, as I said, I spend more than most of my time being a chemist. And I have to admit a complete failure. I'm a physics professor, and my best PhD student declared himself a chemist. I'm not going to talk to him ever again. It's gone.
Thank you.
You did a degree in molecular physics. I failed.
Now I think we will cut short because of lack of time. We have overshooted already. And I invite Dr. Pruthul for a vote of thanks. I see.
We'll talk at dinner. I'll try and persuade you.
So you can be there second. Okay, so after a fascinating talk, and I'm sure there are many ignited minds after this talk, as our Dr. Kalam used to say. It's time to facilitate our speaker, Professor Mason. And to do the honors, I request Professor Vinod Kumar and Professor Joshipura to join. And I also request Director PRL to join them to facilitate Professor Mason with a small memento which they have brought. Yes. Yes. Now, one memento to Director PRL, Professor Bhardwaj from IAPT. Okay. And one more memento for our Dean, Professor Palam Raju from IAPT. Thank you all. Now I request Dr. Pratul Bhai to take the proceedings. Yes, you can come over here.
Finally, we are about to end, and at 5 minutes past it, I feel like I'm 11th man entering the ground in a cricket match. Anyway, I'll make it very short. As a secretary of IAPT RC7, I deem it an honor and privilege to propose a vote of thanks on this momentous occasion. On behalf of IAPT RC7, I convey my deep sense of gratitude and hearty thanks to the Director of PRL, Professor Anil Bhardwaj, for patronizing this flagship program of IAPT. We at IAPT feel proud and honored to be associated with PRL in this joint collaboration, which in 6 years has blossomed into a synergic partnership. Professor Bhardwaj Thank you for your unflinching support and cooperation extended year after year. Also, I would like to extend a special thanks to the distinguished speaker for today, a senior professor, Professor Nigel, for sparing his valuable time and delivering a riveting, exhilarating talk today. I am sure all of us who were in the audience would return home with fond memories of this wonderful occasion. I, being physicist, I am really very proud of it. Could you, Professor Mason, I have one humble request to make. Could you please write an article based on today's lecture? We will be very happy to publish it in our yearly magazine named Pragami Tarang, which is published by our IAPT RC7. A special thanks are due to Professor Ahluwalia, the dynamic president of IAPT, for lending his support and providing guidance, valuable guidance to all the activities carried out by IAPT RC7. A special thanks are due to Professor Pallam Raju, Dean PRL, for curating the entire program and giving it a final shape. Thank you, Professor Pallam Raju, for being there for us. A special thanks are due to Dr. Bhushit Vaishnav, who has over the years been a strong connecting link between us and PRL. Starting from preparing an announcement flyer for the program right up to this day, Dr. Bhushit has taken personal interest in giving this program a wide publicity. Thank you, Bhushit Bhai, for all the help. I would also like to thank Professor B. Sivaraman for taking care of Q&A session on YouTube and all the technical staff at PRL who have made arrangements for live streaming of this entire program. To all those who are present here, I extend a big thank you. Without your presence, this program would not have been so successful. Thank you for turning out in large numbers. Your presence motivates us to do more. Finally, I would also like to thank all those people who have directly or indirectly helped us in making this program a resounding success. Thank you, one and all. Thank you.